Okay, so welcome to this introduction to OpenMP. I'm just going to start off with some introduction overview of the course, what we're going to look at, what we're going to cover, look through the timetable, and some practical information. So we're quite a small group, so please feel free to ask questions at any point. If you can either use the audio or you can type in the chat window. I'll keep an eye on the chat window as we go along and pick up any questions. But please feel free to ask anything as we go along. Okay, so just some administrative stuff. In terms of licensing, this material has a Creative Commons license, which basically means you can copy this and adapt it as long as you give the appropriate credit, and it's entirely free for your own use. So this course is presented under the ARCHER2 training program. So ARCHER2 is run by the UK Research Councils and is run and administered by EPCC and CRAE, who provide the hardware. So for anybody who's not familiar with it, ARCHER2 is the UK's national supercomputing service, which is run by the UK Research Councils. It's at EPCC and University of Edinburgh. We house the machine, we operate it, and we do all the support for it. And CRAE supply the hardware and some operational expertise as well. And so this training is part of a package of training which is provided by the ARCHER2 Computational Science and Engineering Support Team. We do about 60 days a year. In normal times, we would do much more face-to-face courses. We're still largely doing online, but we're going to be gradually transitioning back to more face-to-face training. Okay, very quick overview of the ARCHER2 system. So the full system has just short of 6,000 nodes. There's 128 cores per node, so that's just short of 750,000 cores. Most of those nodes have 256 gigabytes of memory. It uses the CRAE proprietary Slingshot interconnect, and there's various file systems, high-performance file systems attached to that. For this course, so we're just focusing on OpenMP. So we're really just focusing on programming within a single node where we have shared memory available. So we won't be talking at all about how to program multiple nodes in this course. So I see that most of you have signed up for your accounts on Archer. So this afternoon we'll get into the practical sessions. Make sure that you can all get logged in and started on those. Okay, some stuff about EPCC. Okay, I'll skip over that. You can read that at your leisure. Just some pointers to bits of the ARCHER2 website that you might find useful. So the upcoming courses are under, if you just go to the main website, click on the training tab, you'll find the sort of current and upcoming courses there. So in particular, you'll find the link to this course, and if you follow that link, that'll take you to the training materials. So there's PDFs of all my lecture slides, plus the notes for, and code for the exercises are all there. The material from past courses all gets archived. So after this course runs, the material will still remain available essentially indefinitely, at least until the end of the ARCHER2 service. So obviously you're free to take copies of the slides, but if you forget or you want to come back and see something, then the material from this course will continue to be available on the ARCHER2 website going forward. There's also some virtual tutorials, so recordings of those are online, which some might be interested in. And then there's also the documentation. So it might be, if you want to go a little bit beyond what's covered in this course, or you want to do some experimenting, for example, if you want to say use one of the different compilers that's available, or explore a bit more, then you might find it helpful to go and look at the documentation for the system, and that's also all available from the website. Okay, just introduce myself very briefly. My name is Mark Bull. I'm a Senior Research Fellow at EPCC. So as well as teaching on these courses, I'm also involved in education quite heavily. I'm a lecturer on our MSc courses in high performance computing. And I'm also EPCC's representative on the OpenMP Architecture Review Board. So the OpenMP ARB is essentially the body that administers the OpenMP specification. So it maintains the specification document and decides on what new features get added to the API and so on. Okay, at the end of the course, we'll ask you to fill in a feedback form. It's always very helpful for us to know how you've, what your experience of the course has been like, and whether there's things that we can improve. If you have problems with your account on Archer, then obviously you can ask me or one of my colleagues who'll be online during the practical sessions. But outside of that, so obviously we've got 2 sessions today and tomorrow, and then the final sessions next week. So for example, if you have problems with your account, outside of if you want to do some work between now and next week, if you've got problems with your account, then please contact the Archer help desk for that. Okay, so yeah, you've got access to ARCHER2 for the duration of the course. There's a relatively small amount of budget in there, so please don't try and that, which is absolutely plenty to do the exercises, but please don't try and do massive runs of your own programs in these accounts. It'll run out of budget very quickly. Part of the reason for giving you these special accounts, even if you're already an ARCHER2 user, is that these allow us to use a reservation, so we can get quick turnaround on some dedicated compute nodes during the days when the course is running. If you are already an ARCHER2 user, if you prefer to use your existing account, that's absolutely fine. You just won't get access to those reservations, but you can always use the short queue for quick job turnaround. And because for this course we only ever need 1 node at a time, that fits in the time limit is 20 minutes, and that's also plenty for the work for the practical exercises. So you can use the short queue, and you should get reasonably good turnaround time if you want to use your existing account anyway. The accounts will be closed about 2 weeks after the end of the course, at which point all your files, anything that you've done, will be deleted and no longer accessible. So if you want to take copies of anything that you've done, of the code that you've worked on during the course, then please take copies off before the accounts get closed. So all the course materials are available on the ARCHER2 website, and I've said before they'll be archived there for future reference. Okay, just to say that we do have a code of conduct. Just basically says we expect both ourselves and everybody attending to behave themselves and be respectful to other people in the course. Okay. Again, I'll skip over this. If you're interested in funding opportunities for work on application codes, then there's some information here. Okay, so in terms of the timetable for this course, so we'll be doing a mixture of me talking to you and also time for you to work on the practical exercises. And during those times, myself and one of my colleagues, Quevin, will be available online to answer questions and help you. So we can organize like breakout sessions. We can do one-to-one sessions and do screen sharing and so on. So we can support you through doing the practical exercises. So this morning is going to be mainly me talking. So that's at least get you to the stage by beginning of this afternoon, where you're in a position to actually write some OpenMP code. So we'll have a first practical session after lunch today. So make sure that you can all get logged on and up and running and get started on the practical exercises. So same for tomorrow, mixture of lectures and practical sessions, and then next week we'll have a session where we just have one lecture. And then the rest of the day will be dedicated to practical sessions. So I've also put consultancy on here. So, hello? Oh, okay. So that's an opportunity. If you've got your own code that you're working on, if you're interested in using OpenMP or exploring the possible use of OpenMP, or you already started using OpenMP, then that's also an opportunity. I'm very happy to take a look at your code and give you some help with your own application code. So that's an opportunity if you want to think about taking advantage of that for next Tuesday, then please do. I also have I also have a bunch of additional lecture material. So if it's appropriate and people are interested, I have some. I can go into some further topics if those are of interest. I'll ask nearer the time how people want to use those sessions. Okay, yeah, so lecture notes, the easiest way is just go to the ARCHER2 site and follow the links to this course and pick up the materials from there. So, and I'll remind you of this afternoon when we come to it. Although the source code is available on the website, it's easier just to there's a copy of it just on the system, so you don't have to transfer the code. This is basically there's a tar file in a shared directory which you can just copy and unpack for yourselves. So these instructions are also in the exercise notes. So the most important thing is that the file system on ARCHER2 is a little bit strange if you're not familiar with it. When you log on, you arrive in your home directory, but you cannot submit batch jobs from your using files in your home directory. So you also have a work directory which has the same path, except that the home at the beginning is replaced with work. So before you do anything, what I suggest you do is change directory to that work directory and do all your work in there. So I mean, that space is not backed up, but that, for purposes of working on this course, that really doesn't matter. So I suggest what you do is do all your work in the work directory, and then if you want to run batch jobs, then that can happen from your work directory, but you can't submit jobs from your home directory. I realize, it's for purposes of teaching, it's a slight inconvenience. But there are good reasons why the file system is set up like that. Okay, so when you're working on the practical exercises, it's absolutely fine to develop code and test it just by running it from the command line on the login nodes. That's not a problem. However, if you want to actually do accurate timing runs, so if you want to see how your code is performing, then you won't get accurate timing runs by running on the login nodes, because you are sharing those login nodes with lots and lots of other users who may also be running stuff on there. So there's no guarantee you get dedicated access to cores on the login nodes. So if you want to do performance runs, timing runs, then you should use the compute nodes and access them via the batch system. So we've set up some node reservations for this course, and so using those will give you quick turnaround for performance runs. And so these are so you have to specify, if you do that, you have to specify a reservation code. So here are the codes that are set up for this course. So there's a different one for each day. Okay, so that's the overview. Hope you enjoy the course. Please do ask questions. I say we're a relatively small course. There's only 9 or 10 people attending, so please make use of myself and my colleagues to answer any questions you might have. So easiest thing to do is to type in the chat window. Yeah, okay. Any questions? Andrew.
Yes, good morning, Mark. In your introduction, you just went over the features of the Cray system, and you mentioned something called the Cray Slingshot Interconnect. What is that?
So that's the high performance network that connects the nodes together, and so that allows fast communication between the nodes.
So is that a wired connection or a fiber optic connection, or?
So it's actually a mixture of both. So it's a multi-level network. So it's got like it's a hierarchical network. The bottom, if I remember correctly, the bottom 2 levels are copper, and the top level is fiber.
Okay.
It's
Right.
optical. But you just don't notice that, right?
Okay.
Yeah, you know, as far as when you're running jobs on the machine, that's completely the architecture of the network is pretty much completely transparent.
All right. Okay. It was just an unusual phrasing. That's all that I was just curious about it. Thank you.
Yeah. No. So I can point you at more details if you're interested.
Probably not at this stage.
Probably not. Okay. So yeah, we won't. I mean, it's, you know, for OpenMP, it's of no interest because OpenMP only runs inside a node, so we're not using not using
Right.
the network.
Okay, that's good to know.
Yeah. Okay, great. Any other questions? Okay.
Yeah.
If not, then
Hello.
Hi.
Hi. So the first step is go through the PDFs and then put our hands on the GitHub lessons.
Yeah, so I'll be going through the first 3 lectures for the rest of this morning, and then this afternoon you will have the opportunity to get your hands on and start doing some programming.
Okay, thank you.
Great. Okay, so I'll press on with the first lecture then. So what I'm going to do here is basically cover the fundamental concepts to do with shared memory programming and threaded programming. So I won't really be talking specifically about OpenMP yet. I really want to make sure you're all familiar with the underlying concepts that OpenMP is built on. So what I'm saying here really applies to not only to OpenMP, but also to other multi-threaded programming interfaces. Things like POSIX threads or C++ threads, or even things in other languages like non-HPC languages like Java threads, for example. Okay, so I'm going to start off by just saying something very briefly about hardware, about shared memory systems, to make sure that we have a basic understanding of the hardware that we're considering programming with these interfaces, and then talk about more about the software concepts in threaded programming. So let's start off looking at shared memory systems. So multi-threaded programming is most often used on shared memory parallel computers. So at basic level, what's one of those? It's a computer that consists of a number of separate processing units. some CPUs or cores, together with some memory. So that's pretty much any computer that you come across nowadays, because everything is multi-core. So even even your laptop probably has 4 or 8 cores in it these days. But the key feature of shared memory systems is that there is a single address space across the whole memory system. So what does that mean? It means that every CPU or core is able to read and write all the memory locations in the system. So every CPU has direct access to all the memory just by doing reads and writes, or at a lower level, if you like, issuing load and store instructions. So there really is one logical memory space across the whole machine. And another way of thinking about it is that all CPUs or cores refer to a given memory location using the same address. So there's a single address that all the compute units can use to refer to a memory location. So conceptually, it looks like this. Let me get myself a. I'll give myself a pointer. No, okay. There we go. Okay, so conceptually, the system looks like this. So we have a bunch of processors or cores, a bunch of processing units, and they're all connected in some way to some global piece of global memory. Okay, some memory that stores all the data that the system contains. So that's kind of the logical model that we're thinking about when we're programming. So we have one memory, lots of processors. Of course, real hardware is a lot more complicated than this. So in particular, the memory itself may be split up into multiple smaller units. There may be multiple levels of cache memory, and some of those levels of cache memory may be shared between subsets of those processors. And that interconnect may have some more complicated topology. But nevertheless, if it's a shared memory system, a single address space is still supported. So what that means is that all that hardware complexity is certainly there, and it can affect the performance of programs, but not their correctness. Okay, so you basically have a guarantee that if you write a correct OpenMP program, then the hardware ensures that that program will always execute correctly, regardless of all this hardware complexity. However, that's this complexity may have some, and in some cases quite significant, impacts on performance. And we'll talk a bit about performance issues in OpenMP next week. Okay, so even this is highly simplified, but it just shows some of the potential extra complexity features. Okay, so for example, you might not have one piece of memory. The memory might be split up into multiple pieces. So each memory may have some set of processing units which are more closely associated with it at a physical level. So the two processing units on the right might be physically located closer to the right-hand piece of memory. And then each of those processing units might have, say, its own level 1 cache, and then you might have a shared level 2 cache. And then these the processing units and the memory are all connected together somehow. But nevertheless, it still means that any of these processors are still able to access any memory location. So the performance of those memory accesses may be different depending on where the physical memory and the physical processor are located in the system, but nevertheless, it still supports this single address space, which allows us to use this multi-threaded programming model. So in reality, of course, modern systems are much bigger. So for example, if we look at what's in ARCHER2, then each node in ARCHER2 has 2 sockets. Each socket consists of is a chip with 64 cores, and the memory itself is actually, so the memory across the whole node is really split up into 8 separate memories. So essentially each piece of memory has 16 cores associated with it. And then every core has its own level 1 and level 2 cache, and every set of 4 cores shares a level 3 cache. So it's really quite a complicated and hierarchical memory system, and that's getting fairly typical of what we're seeing in supercomputers these days. We're seeing nodes, very powerful nodes with lots of cores and very complicated hierarchical memory systems. So I say, all that complexity does have impacts on performance. We will potentially see some of that. We'll certainly talk about some of those issues next week. But say as long as it doesn't impact how you write performance in terms of correctness. It's guaranteed that whichever cores your program happens to be using, whichever memory happens to contain your program's data, everything still works. Okay? At least your program will execute correctly. Performance is another matter. Okay, does anybody have any questions about the hardware? So that's it's just a very simplistic or basic view of the type of hardware we're looking at and what we can expect from it. Okay, so let's now start thinking more at the software level. So the programming model that we're talking about here is based on the notion of threads. So essentially, threads are like processes, except that threads can share memory with each other, as well as having their own private memory. So unless you do something very special, separate processes will not share memory with each other. Every process has its own separate memory space. This is not physical memory. This is logical virtual memory. But so processes cannot by default share memory. So threads are different in that they can by default have access to some shared memory which they can all access. So that means essentially that program data comes in two types. There is some shared data which can be accessed by all the threads in the program, and then every thread has some private data which can only be accessed by the owning thread. Well, at least logically anyway. It may be technically possible to access another thread's private data, but that's a really, really bad thing to do. And OpenMP, for example, this OpenMP specification specifically says, if you try to do that, then that's not a correct OpenMP program, and anything might happen. And because at some level, it's all just memory. But there's this kind of logical distinction between shared data and private data. Okay, and then to do useful parallel programming, what happens is that essentially what can be done is that different threads can follow different flows of control through the same program. And each thread essentially has its own program counter. Each thread has its own individual notion of which instruction it's going to execute next. So Andrew asks, is this idea similar to class objects in object-oriented programming? The answer is no. Unfortunately, the same terminology is used, okay, or similar terminology is used. In object-oriented programming, have these notions of private and public data for an object. Okay, but this is not the same thing. Okay, this is to do with the accessibility of data from different threads. Yeah, it's same or very similar terminology, but used to mean something rather different here. Okay, so usually when we're doing high performance computing, we're normally thinking about having a one-to-one mapping between the threads and the hardware execution units. So we would normally be thinking about running one thread per core. That would be the normal thing to do. It could be more. And indeed, a lot of modern processors do have hardware support for running multiple threads on a core. However, that is usually not the default, or is disabled by default in many systems, because usually it doesn't help performance for scientific programs. There often is a way, if you really want to do it, if you want to run 2 threads per core, for example, on ARCHER2, there is a way of doing it. But in 99% of cases, it's not going to improve your performance. So it's basically disabled by default. Okay, so just to give some sense of this in a sort of pictorial form, if we can have multiple threads, so every thread, for example, has its own program counter. So every thread has its own notion of which instruction it's going to execute next. So every thread is following a different flow potentially a different flow of control through the program, and is completely unaware of what other threads are executing. Each thread has some private data, to which only it has access, but then all the threads have access to some shared data in the program. Okay, so that brings us on to the idea about thread communication, because in order to have useful parallel programs, or at least non-trivial parallel programs, we need threads to be able to communicate and exchange data with each other. And very simply, that happens by reading and writing shared data. So if I have two threads and I want to transmit some data from one to the other, then the way that happens is that thread 1, for example, might write some value in a shared variable, let's call it A, and then at some point later, thread 2 can read the value from that same shared variable A. Okay, so they both have access to that shared data. So the important thing to take away from this is that in this programming model, there is no notion of messages. Okay? So if you're familiar with message passing programming, then that's not what's happening here. There is no concept of threads don't send messages to each other. If they want to communicate, they do so only by reading and writing values in the shared data space. Okay, so let's give a very simple example of how this works. So suppose I have two threads, thread 1 and thread 2, and each has their own private data, and there's some shared data here as well. So for example, what might happen is that sort of thread 1 might write a value, say 23, into a variable called myA, which happens to live in the private data space. Exactly how that's arranged depends on the API, and we'll be discussing about how that works in OpenMP very soon. But let's just assume that that's the case for now. So myA happens to lie in the private data for thread 1. It can then say copy that value into A, which lives in the shared data space. And then at some point later, thread 2 can then read A, and then maybe wants to do some computation with it, and then store the result in myA. So this copy of myA lives in thread 2's data space. So you can see that we've got these two different types of data. So A lives in the shared data space. There only is one copy of it, and all the threads have access to it. myA lives in the private data space. So every thread has their own copy, and those copies are independent of each other. So they can contain different values, and they will in general contain different values, even though the threads refer to it by the same name, refer to those variables by the same name. Okay. So if you something that might have occurred to you there is, well, how do we arrange for, if we want to communicate a value from thread 1 to thread 2, how do we make sure that the write from thread 1 happens before the read from thread 2? And how do we make sure that those accesses actually occur in the correct order, and that thread 2 doesn't try to read A before thread 1 has written it? So that brings us on to the idea of thread synchronization. So because by default, the threads are executing asynchronously. So the threads just proceed through program execution on their own without any regard for what other threads may be doing. Okay, so each thread proceeds through its program instructions independently of the other threads. So that means that we have to do something to make sure that actions on shared variables do in fact occur in the correct order. So for example, thread, the example we've been talking about, thread 1 must write variable A before thread 2 reads it. But sometimes we have dependencies, data dependencies the other way around. We might want, for example, that thread 1 wants to read the old value in variable A before thread 2 writes something new into it. So we can have dependencies both ways around. The other important thing to recognize is that if we have something in our program that makes an update or modification to a shared variable, so for example, if we have a shared variable A and we add 1 to it, then by default those actions are not indivisible atomic actions. And that's because if you think what's happening at the assembly code level, then that's doing an update requires at least 3 different instructions to happen. Okay, it requires a load of A from memory into the registers on the core. Then it requires the actual add instruction, which will produce the result probably in another register on the core, and then a store instruction to put the result from the register back into memory. Okay. So by default, what happens if 2 threads both try to do this at the same time? So if 2 threads both trying to add 1 to A without any synchronization, then those instructions can get interleaved in time in a way that one of those updates may get overwritten. Let's just walk through how that might happen. Okay. So here I'm really thinking about, I'm no longer thinking about the logical shared and private data spaces. I'm really thinking about what's going on at the hardware level here. Okay, and so what do we have? So we have, now thinking about two separate cores. Each core has its own CPU registers, and they're able to load and store values into physical memory here. Okay, I'm ignoring any cache memory here because that turns out to be not relevant to this argument. Okay, so I suppose I have a thread running on each of these cores, and they both try to add 1 to some shared variable A. So A starts out in memory, okay, with the value 10, and then what might happen, for example, is that the first thing that happens is that core 1 loads A. So it gets a copy in its registers, and then so does core 2. Core 1 does the addition, so its value in registers is now 11, but the value in memory is still 10. So and then core 2 does the addition, okay, and then you can probably start to see what's going to go wrong here. Core 1 stores the value back into memory. So memory now has the value as 11. And then finally, core 2 stores its value back into memory. Okay. Problem. Okay. So we started off with the value 10. We had 2 threads adding 1 to it, and we end up with the value 11. So that's the sort of problem that can happen if we don't correctly synchronize threaded programs. And essentially, at essence, it's this problem or variations of this problem that make multi-threaded programming difficult and error-prone. Okay? because we constantly have to guard against problems like this happening. Because it's up to us as programmers to ensure that actions on shared variables are correctly synchronized. The hardware does not take care of that for us. So Andrew asks, does this require the use of a master thread? So OpenMP does have the concept of the master thread, but that's not necessary. So this problem occurs in any threading model, even if there isn't really the notion of a master thread. Yeah, you should be seeing my slides on the screen. Anybody else not seeing my slides?
No, it works fine.
Okay. Oh, okay. I'm not sure what's going wrong then. If you can't see my slides, are you seeing my video?
Hi. Yeah, I can see your video, but I can't see the slides. Maybe I'll just try to see if maybe there's some access over here from my end, which I've not done. I'll just try to check and get back to you.
Okay. So that's okay if you follow on. Obviously you can follow on the downloaded copy, but that's not as good as that's not as convenient, obviously. Okay, so I think it may be a problem at your end. Let's see if you can figure it out. Okay, thank you. So this type of problem is an example of what's called a race condition. So the technical definition is this is what happens if multiple threads access the same memory location without any synchronization, and at least one of those accesses is a write. So at least one of those accesses is going to change the value. So if they're all just reading, it's fine, there's no problem. But if at least one of the threads is an access and there's no synchronization, then this is what's called a race condition. And so if we don't have any synchronization, then different time orderings of those accesses may occur, and that possibly results in non-deterministic behavior of your program. So this is very unpleasant, because what it means in practice is that running the same program with the same inputs twice may give you different results. Okay. So it's a very nasty type of bug. It's worse than your normal sequential programming bugs. And in particular, it's not reliably detectable by conventional software testing procedures. So your standard software engineering practices of writing test suites and that kind of thing will not necessarily pick up this kind of problem. It may be the fact that that it gives you, if you run the program 100 times, it gives you the correct answer 99 times and the wrong answer once. So wrong answers may be rare and therefore difficult to observe with normal testing. So in essence, this problem is what makes multi-threaded programming difficult, conceptually difficult, and potentially error-prone. And that's the challenge that we face. I mean, all parallel programming is hard. Okay, so but there's no, they're just different styles of parallel programming are just hard in different ways. And essentially, when we do multi-threaded programming, this is the essence of the difficulties is essentially dealing with or guarding against race conditions. Andrew says, no tools like file locking or rollback. So there are, so we have synchronization constructs, and we do have sort of the equivalent of locks in the sense that we are able to lock access to variables or lock access to blocks of code. So that's an important synchronization technique. We don't have rollback. Okay. Because essentially that's too expensive to implement. We can't. There is some hardware support for speculative execution, but and that essentially is not used at the programming level. Okay, it's essentially used to help make the synchronization constructs more efficient, but they don't typically appear at the programming interface level. But we'll talk soon about essentially the different types of synchronization that we have available to us. So there are several. Okay, so I just wanted to cover a few more concepts before we move on to talking about OpenMP specifically. I want to talk about tasks. So a task is really quite simply a piece of computation which can be executed independently of other tasks. And when we're doing parallel programming, that's essentially what we're trying to do, is we're trying to identify tasks. So pieces of independent computation. And with the idea that different threads can execute different tasks at the same time. So in principle, what we could do is create a new thread to execute every task. Okay, so we could have we could conceptually have a one-to-one mapping between these independent pieces of computation and the actual threads. But in practice, that ends up being too expensive because creating threads comes with some cost. So especially if we end up with if our program naturally has large numbers of small tasks which don't take very long to execute, then creating a thread for every task would be way too expensive. Instead, the way it typically works is that tasks can be executed by some pre-existing pool of threads. So what typically happens is that we will create a fixed number of threads at the start of the program, and that number of threads will typically be mapped to our hardware resources. Okay, so again, this is the idea that we essentially want to run one thread, probably one thread per core. So the pool of threads that gets created at the beginning of the program, the number of threads will probably be matched to the available hardware resources. And then what happens is that essentially, tasks can be submitted to this pool of threads. Some thread in the pool will execute the task. As a programmer, we may not have much or any control as to which thread does which task. And then at some point in the future, that task is guaranteed to have completed. And we can also think about having ordering between tasks. So tasks may or may not be ordered with respect to other tasks. There are maybe ways to specify to say that task 2 cannot execute until task 1 has finished, or ideas similar to that. OpenMP does have support for explicit support for task-based programming. I'm not going to cover it in this course unless it's something that I do as an extra piece of as an extra thing next Tuesday, if people are interested in it. It's not that widely used. I say it exists in OpenMP. It's potentially useful, but it won't be your sort of first. It won't be the first thing you want to try with OpenMP for the vast majority of applications. Okay. Something that's much the sort of pattern that occurs much more commonly are parallel loops, because loops turn out to be the main source of parallelism in many applications, particularly scientific applications. And if the idea here is really very simple, but also very powerful. If the iterations of a loop are independent, in other words, they can be done in any order without affecting the result, then we can share out iterations between different threads. Okay. So, for example, if I have a loop like this, so it basically just adds the elements of 2 arrays together. So if we have a loop like that, then every iteration of that loop can be executed independently. It doesn't matter what order we do those additions in. Then, for example, we could do the first 50 iterations on one thread and the second 50 iterations on another thread. So we can simply divide up the iterations across multiple threads. Okay. Don't want you to get the wrong impression here. In practice, this loop contained far too little work to be worth executing on multiple threads. If I had 100,000 iterations instead of 100, then I might be able to do something useful with multiple threads. But certainly not a simple operation like this at the scale of 100. Would need tens or hundreds of thousands of iterations to make it actually worthwhile parallelizing a loop like this. So essentially, conceptually here, we can think of an iteration or maybe a set of iterations as a task. Okay, So we have we can think of a set of iterations as an independent piece of computation, and different sets of iterations can be executed by different threads. Okay, and the last idea I want to introduce to you in this lecture is the idea of reductions. Okay. So reductions are these operations that produce a single value from associative operations like addition, multiplication, maximum, minimum, logical and, logical or. So addition is by far the most common one, and then probably maximum and minimums are the other ones you're likely to come across in practice. So for example, if I have a loop like this where I just want to I want to form the sum of the elements of an array in a scalar variable b, then the question is, can I extract some useful parallelism from that? Well, if I divide those iterations between different threads, then I would have a race condition. If b is a shared variable, then I would have multiple threads trying to update b. Excuse me. I would have multiple threads trying to update b without any synchronization. I've got a race condition. I've got non-deterministic behavior. On the other hand, if I use some synchronization and only allow one thread at a time to update b, then that would effectively remove all the parallelism. And in practice, the overheads of doing the synchronization would mean that that I would actually get worse performance than just executing the loop sequentially. Clearly, there's an obvious solution here. If instead each thread can accumulate its own private copy, and then at the end of the loop, those private copies are reduced, so in this case, added together to give the final result. So if I can arrange for each thread to have its own copy of b, and then at the end of the loop, we add those copies together to get the final result, then provided the number of operations, provided the number of iterations in the loop is much bigger than the number of threads, then almost all those operations can proceed in parallel. And we have a small number of operations of order the number of threads, which will essentially be sequentialized or synchronized at the end. So we can extract we can extract a lot of parallelism from this example, from this kind of pattern, if we do the right thing. So can I explain why the race condition would? Yeah. Okay. So what happens is, suppose what happens if b is a shared variable. So b lies in the shared data space, and we divide the loop iterations up between the threads. Then I have essentially exactly that same update problem that I talked through in the example before. We have two threads, we have multiple threads trying to modify, trying to add values to the same shared memory location. So that's an example of race conditioning. It's exactly analogous to or just a slightly extended example of two threads trying to add one to a shared variable. Okay, great. Andrew.
Yeah, so just running with this illustration here. So if you've split your processes up so that you can run on multiple threads, and each thread stores a private copy of its results for each part of that split process, That means then each of those private results would first then need to be copied to the shared memory before they could be all summed together. Would that be right?
No, you could directly add. You can add a private. You can add a private variable into a shared variable directly. You would not.
All right. Okay.
There are different ways of there are different ways of implementing this. Okay.
Okay.
So you can either directly add into a shared variable with the appropriate synchronization. Okay. So as long as you have, as long as you make some guarantee that only one thread at a time is doing those additions, that's one way of doing it. Another way would be to use shared memory. So, for example, you could have a shared array where each thread wrote into a different element of the array.
Yeah. Okay.
And then after everything's finished, okay. So I have to guarantee that I have to have some way of guarantee that all the threads have finished finished writing. Then one of the threads could then access that shared array and add up all the elements.
Okay. Yeah.
Okay.
So
there are various different ways that you could potentially handle this. In practice, neither of those is actually the most efficient. Okay. What you would actually do or what an OpenMP implementation would, because OpenMP supports doing this for you. Okay. So what an OpenMP implementation and under the hood would actually do is some sort of tree-based algorithm. Okay.
Right.
So use a binary or maybe 3-array or 4-array tree structure to do this. And yeah, so there are more sophisticated ways of handling this this problem.
Okay. No, you have to forgive me. My mind is sort of racing ahead here.
Yeah, sure. No, that's no problem. Let's say, yeah, I'll certainly talk about how OpenMP supports supports this at the syntax level. I won't necessarily tell you, unless you ask me, I'm not going to tell you how it's done under the hood. Right?
All right, thanks.
But I'm happy to discuss it, right? Absolutely, yeah. So in practice, there are reasonably sophisticated ways of making this efficient. So that effectively you can do it in, if I have p threads, then there are ways of doing this in order log p time, whereas this sort of simple ways of doing it are order p. And that starts to matter for relatively modest numbers of threads, actually. Okay, so as a picture, you don't know how to share it. You can't share it unless I let you. Okay, for tree-based reduction. Okay. Do you have a link? Post a link in the chat. If you want. Good. So now I'm going to talk about OpenMP specifically. Again, it's really just at a conceptual level, going to get into how OpenMP works and implements some of the concepts that we've talked about without really getting into much actual syntax yet. That'll come after coffee break. So I'm going to talk about some of the basic concepts in OpenMP, and I'll say something very briefly about the history of OpenMP, and then some practical stuff about compiling and running OpenMP programs. Okay, so what is this OpenMP thing anyway? So it's an API which is designed for programming shared memory parallel computers. So it uses the concept of threads and tasks, which I already introduced you to. It is a set of extensions to Fortran, C, and C++. And those extensions consist of 3 different types of things. So the most important one is compiler directives, but there are also runtime library routines, and there are also environment variables. And we'll be talking about all of those at some point. Okay, but let's start off with directives, because most of the API is in fact directives. Okay, so a directive is effectively a special line of source code with meaning only to certain compilers. So it's designed to be extra lines of source code that can be activated, in this case, by compiling with an OpenMP aware compiler. And the directive is distinguished by what's called a sentinel at the start of the line. So that's just a special sequence of characters which indicates that this is an OpenMP directive and is not a statement or line in the underlying base language. Okay, so OpenMP sentinels are for Fortran, $OMP, and for C or C++, #pragma-OMP. And the reason that they look like this is that it means that these directives will get ignored if you compile the code just as regular sequential Fortran C or C++. Okay, so Fortran compiler will treat that as a comment if OpenMP is not enabled, and the essentially the C preprocessor will ignore those will ignore #pragma-OMP. We'll just treat it as an unknown preprocessor pragma and ignore it. Why is it done like this? Well, it's the intention here is that it doesn't guarantee, but it provides support for the ability to write code that functions correctly, both as a sequential code and as a parallel OpenMP code. Okay, so you can have the same source code that can function correctly in both ways, both as plain old sequential code and as parallel OpenMP code. In practice, you have to work a little bit harder to make sure that's the case, but the design of the sentinels certainly goes some way to helping that. This is useful just from a software engineering point of view. It allows you to maintain a single base of source code that functions correctly in both modes. So that can be pretty useful from a software engineering point of view. So you can effectively compile the same code with and without OpenMP as required. Actually, this would be a good point for me to ask, do we have any Fortran programmers on the course today? Yes, okay. Good. Okay, at least 2. that's fine. So most of my, a good number of my examples are in, I have both C and Fortran versions. So I will, for this course, I will not skip the Fortran stuff. Okay. Sometimes we just don't. Sometimes I just don't get any Fortran programmers on these courses, and but in this case we do. So I will make sure that I cover the Fortran stuff. For the most part, there isn't really, apart from the syntax, there are very few differences in OpenMP between Fortran and C. But I will point out where they do differ, and you can also for the practical exercises, you also have the choice of doing them either in Fortran or C. So whichever you prefer. Great. So let's talk about how OpenMP works at a basic level then. So that means talking about parallel regions. So parallel region is the basic fundamental parallel construct in OpenMP. So all parallelism in OpenMP relies on the existence of parallel regions. What's a parallel region? Well, a parallel region defines a section of your program. And the way that OpenMP works is that your program always begins execution on a single thread only, which is called the master thread, or at least it used to be, and I'm still using that terminology. OpenMP is now has actually dropped that terminology. I think it calls it the main thread these days. So I should probably update my my material to be more politically correct. But you'll still hear this terminology around, and my apologies for still using it. So your program always begins execution on a single thread, and only when the first parallel region is encountered, then at least logically, the master thread will create a team of threads. So this is what's called a fork join model of parallelism. If that doesn't mean anything to you, that doesn't matter, okay? But if you've heard it before and that makes some sense, then great. Once we're inside the parallel region, every thread then executes the code statements which are inside the parallel region. And then at the end of the parallel region, the master thread waits for all the other threads to finish, and then it continues sequential execution of the next statements in the program until we get to the next parallel region. So it might help to think about this more sort of more visually. So here is our program, okay, and some sort of sneak preview of some syntax, okay. So when our program starts executing, we are executing on a single thread, and only when we get to the first parallel region in the code. So in Fortran, parallel region is a block of code between parallel and end parallel directives. In C or C++, it's essentially a block of code in curly braces following a hash pragma OMP parallel directive. In both cases, this piece of code in here is the parallel region. At this point, logically what happens is that the master thread creates a team of threads. So in this case, I've shown a total of 8 threads. The master thread itself executes the parallel region together with the additional 7 other threads. So all those threads execute the block of code inside the parallel region. At the end of this block of code, the master thread waits until all the other threads have also reached that point. So effectively, there's a synchronization point at the end of the parallel region. The master thread then carries on executing on its own. So we're back in what OpenMP calls the sequential part of the program. And then we can repeat this process as many times as we like during the lifetime of the program. So a real OpenMP program might, could execute millions of parallel regions during its lifetime. Okay. So I've kind of been careful and to say that what happens is that logically, the master thread creates a team of threads. But I also introduced this notion of a thread pool earlier. So in practice, what OpenMP implementations really do is create a thread pool at the very beginning of the program, and then use that thread pool to execute every parallel region. So the real, if you like, or the underlying operating system kernel threads that are executing your OpenMP parallel program are not in practice created and destroyed for every parallel region. In practice, they are created once at the start of program execution and then reused for all the parallel regions. Now, it's possible that the program might at some point ask for additional threads, in which case they have to be created and added to the pool. But the most common use case is for a program to use a fixed number of threads for every parallel region. So that's not a restriction of OpenMP. That's just the common practice. And again, it's really down to the fact that you probably have a fixed amount of hardware resource to use, and therefore you want to essentially create your pool of threads based on the available hardware resources which you have available for the execution of your whole program. So that's the typical scenario that we have on so either on supercomputers, or if you're running on your own, even if you're running on your own laptop or desktop system, you've got a fixed dedicated amount of hardware resource. You've got a fixed number of cores to use for the lifetime of your application run. So it makes sense to create those threads once and reuse them, which is cheaper than actually destroying them and recreating them all the time. Okay, any questions about that? Okay, so Andrew, go ahead.
Yeah, so just a quick question then. So is it possible, again, maybe it's just jumping ahead, that with the master thread running, it spawns off these parallel processes. Is it possible for one of those parallel processes then just to get stuck, and then the whole thing just gets stuck?
Yeah, sure. Yeah, if you're not, I mean, you can, if one of those threads for example, if one of the threads goes into an infinite loop, for example, okay, then the master thread will just wait forever at the end of the parallel region. So it will also get stuck. And in fact, all the other threads will just get stuck at the end of the parallel region.
Right. So I presume then there's a way of actually tracking those process IDs for those threads?
No, not really. I mean, at the operating system, all the threads belong to the same process.
Right.
Okay, so you've basically got one process running multiple threads. Well, that's slightly dependent on which operating system, but let's assume we're talking either Linux or Windows here.
Yeah.
So that's the way they're structured. Okay. So if you kill a process, then all its threads will die.
Right. So the only way you'll find out you've got a problem then along one of the threads is when the whole sort of master times out. Right. Okay.
Well, it won't even times out. I mean, typically it'll just hang there forever, right?
Right.
It'll most OpenMP implementations are not really designed to be, shall we say, fault tolerant or fault aware in any meaningful way. Okay, so if you code something, if you code something bad, then you can just result in your program can just deadlock and hang forever.
Right. Okay. That's scary.
Yeah, sure, but it's not really different. Yeah, it's okay. Right? I mean,
right.
if you're running interactively, you will notice and you could kill it. Okay, if you're running in a batch scenario, then eventually your batch job will time out and everything will get cleaned up for you.
Right.
So it's generally not you have to work quite hard to be to leave stuff lying around running and not notice, because and again, as soon as if you're running on a command, on an interactive terminal, as soon as that process dies, as soon as you log out or it times out, then any process that you were running gets killed as well.
Right.
So in practice, you don't have to worry too much about leaving stuff lying around.
Okay.
There are always corner cases. There are corner cases where it might happen, but mostly you don't.
I'm just reminded of my early experience in threading processes, and that was actually at Edinburgh. When I was at Edinburgh, I managed to bring a compute server to a grinding halt, apparently, and got really told off about this stuff.
If you try hard enough, you can probably do it. These days, operating systems are pretty resilient to you trying to do that kind of thing.
Right. That's good to know.
It wasn't necessarily the case in the past. It was definitely possible that, or more common that, processes didn't get cleaned up properly, and you could end up with basically zombie processes still running for days, and nobody noticing.
Thanks.
Yeah. It's not impossible, but it's quite hard to do, and you shouldn't overly worry about it. Okay, Sahil. Okay. Okay, has answered his own question, I think. Yes. Okay. So so typically what happens at the operating system is that you have a single process which contains multiple threads. And so that's what's running your OpenMP program. It's one operating system process, which then creates multiple threads inside itself. that's the way it's implemented. So OpenMP specification never talks about processes. Okay, it only talks about threads. So for logical purposes, OpenMP only has threads, but in practice at the operating system, all those threads belong to the same process, same operating system process. And the distinction gets important when we start thinking about, and this is an entirely legitimate programming technique, is to combine message passing, so combine MPI and OpenMP in the same application code. In which case, then every MPI rank is essentially its own process. And then every MPI process then creates its own OpenMP threads. Right, so shared and private data. Okay, so how does that work? Well, what happens is that when we're inside a parallel region, then variables can either be shared or private. Okay, and that behaves how you expect. All threads see the same copy of shared variables. All threads can read or write shared variables. So each thread then has its own copy of private variables, and those are invisible to other threads. Again, at least as I hinted before, in practice, then that may not be. You can if you work hard enough, you can circumvent that. But on your own head, be it. It's a very, very bad idea, and the OpenMP specification says you must not do this, or at least there are no guarantees to what happens if you try to do this. But it's not difficult to try and do it. For example, if you, especially in C or C++, if you take a take a pointer to a private variable, put the value of that pointer into a shared variable, then some other thread can read the value of that pointer and try to access that memory. Okay, in practice that probably works, right? Because again, because of this process thread structure, in fact, the thread's private data is in fact just the stack space associated with the thread. They're all part of the same process, so the operating system does not implement any protection between different threads' private data in practice. So yeah, it's technically possible to do it, but you should acknowledge that fact and never think about it again effectively. A private variable, you should think about private variables as variables that can only be read or written by its own thread. Okay, yeah, so it's it may in fact be possible to access, technically possible to access other threads' private data, but it's you've no idea what's going to happen, and you will also confuse the hell out of anybody who's trying to understand your code, probably including you at some point in the future. Okay, so we talked about parallel loops, and they're clearly very important. If I had to take a guess, you say if you took all the OpenMP code in the world and said what does it do, then probably I would think greater than 95% of it is doing parallel loops. It's just the sort of the absolute common pattern of parallelism that cropped up everywhere in all applications. So parallel loops are really important. But if we're inside a parallel region, then in fact all threads are in fact executing the same code. So OpenMP is slightly odd like this, is the sense if we just use parallel regions, then we're in fact duplicating the same code across all the threads. And that's for doing parallel loops, that's not particularly useful. So OpenMP also has directives that indicate that work should be divided up between threads rather than replicated, because replicated is, if you like, is the default behavior. And in OpenMP, this is called work sharing. And say, because loops are main source of parallelism everywhere, OpenMP has a lot of support for parallelizing loops, and we will talk in detail about how that works this afternoon. So for example, there are a number of options to control which loop iterations are executed by which threads and so on. However, it's important to realize that it is up to us as programmers to ensure that the iterations of parallel loop are independent. So OpenMP does not automatically attempt to check that, okay? So it will, if you you can just code race conditions if the iterations of your loop are not in fact independent, you just end up with a race condition. So OpenMP will do nothing to try and alert you to the fact that you've done something wrong in that case. There is a restriction here, so only loops where this style of parallelism only works for loops where the iteration count can be computed before the execution of the loop begins. Okay. So the number of iterations doesn't need to be known at compile time. So it doesn't need to be hard coded into your or known at when the code compiles. It has to be computable before. It just has to be computable before the loop starts executing. And so general while loops can't be handled like this. There are other ways of handling those in OpenMP, using tasks, but that is a restriction on this style of parallelism. Okay, so synchronization. What tools do we have to synchronize threads and protect ourselves against race conditions? Well, there are quite a few, but the main ones that OpenMP uses are, well, first and foremost, the barrier. So a barrier is a full synchronization point across all the threads. So this is a point in the program where all the threads must arrive at a barrier before any thread can proceed past it. So yeah, it's a full synchronization between all the threads executing in the parallel region. So effectively, that's what's happening at the end of a parallel region. When the master thread waits for all the other threads, that's effectively a type of barrier synchronization, or an instance of barrier synchronization. And by default, we also get barrier synchronization at the end of a parallel loop by default. Okay, so Andrew has a question. So this means, yeah, for is better than while or repeat. Yeah, basically, we have to use it for this style of parallelization. Basically, you have to use for loops. And in fact, if we're in C or C++, for loops are actually general while loops, really. So there are actually some additional restrictions on what you're allowed to do on the form of those, on the form of for loops, which can be parallelized using OpenMP work sharing constructs. Okay, so we've got barriers, full synchronization points. We have critical regions. So this is a critical region is a section of code which only one thread at a time is allowed to enter and execute. So this is essentially something that we can use to protect the modification of shared variables. So if we have this kind of situation where we want multiple threads to update the same shared memory location, we can use a critical region, which means that only one thread at a time is allowed to do that. And if a thread arrives at a critical region where there's already a thread executing, it will just wait its turn to execute that block of code. And the third type is similar but subtly different, okay, which is atomic access. And that's so a critical region can contain any arbitrary piece of code. Atomic accesses apply just to an update or a read or a write of a variable, which is allowed to be only performed by one thread at a time. And again, this is also useful for doing modification of shared variables, but it's a more special case than critical regions. And there is a subtle difference here in that really what's happening is a critical region is protecting access to a block of code, whereas atomic accesses are really protecting accesses to actual memory locations. So there is a subtle difference there, which we'll talk more about later on. But those are the three main or commonly used methods of synchronizing threads in OpenMP. There are others we will talk about. There are arbitrary locks. There are locks as well, and we will cover those. Okay. Any other questions before I dive off into a quick history lesson? Okay, so yeah, where did OpenMP come from? So Cheryl asked, does Fortran have these critical regions, etc.? So Fortran does not, but the OpenMP extensions to Fortran do. Yeah. So everything I've talked about so far is not, about OpenMP is not dependent on the base language. Fortran itself is a little bit weird because it does the Fortran specification itself does have some parallel constructs in it. It has do concurrent. Okay. It has coarrays. So Fortran standard does contain some parallel constructs which are separate from OpenMP. But the OpenMP interface for Fortran does have all this stuff, yeah. Okay, so where OpenMP came from? Well, this style of programming is actually very old, okay? It really goes back to at least to the sort of late sort of Cray vector machines, which were around in the sort of late 1970s, early 1980s. And in the sort of 1980s and 90s, this kind of machine became quite popular. But what happened was that every hardware vendor provided a different API for doing it, okay? Essentially for doing parallel loops. They were mainly directive based. They were almost all Fortran specific because that's the language that everybody used at the time, but it made it pretty hard to write portable code. So every hardware vendor provided their own compiler with their own set of directives for doing parallel loops, essentially. So the basic idea was OpenMP would say, okay, let's standardize this and have everybody do it the same way. So a bunch of companies set up the OpenMP architecture review board. These days, it includes most major hardware vendors, also compiler vendors or compiler writers, and a bunch of academic organizations, including EPCC and some of the large US government labs, for example, are also involved in the specification process. So the first OpenMP standard dates back to 1997, and then there have been a bunch of versions since then. So it's grown a lot. Kind of one of the most important things that happened was that originally there were separate specifications for Fortran and for C and C++, that those got merged together. And so we're now up to version 5.2, which has, is now very big, includes a lot of extra features like tasks. It also includes features for offloading computations onto accelerated devices like GPUs. Again, that's a whole topic in itself, which I'm not covering in this course. So in practice, what you'll find is that most current implementations comply with either 4.5 or 5.x, except for the offloading stuff, which is a bit more, has less widespread support. So again, it depends on the compiler and the hardware platform whether you have support for offloading to GPUs available or not. But apart from that, then the compliance is generally pretty good across compilers. As I say, there may be cases where there's stuff in 5.1 or 5.2 that may or may not be in current versions, but those differences are thankfully pretty minor. So you will, unless you're really operating unless you're doing offloading or really operating with trying to use the very latest features, you will find that OpenMP compilers do a good job of supporting everything that's in the specification. Okay. Resources. Okay, so OpenMP has its own website. The most useful thing there, or potentially useful thing there, I guess, is you can look at the full language specifications if you want. In the past, I kind of encouraged people to do that because they were quite readable. These days, the specification has got so big and the terminology has got so complicated and interdependent on other terms that actually the full specification is quite difficult to read these days. That's a bit sad and unfortunate, but that's the way it is. I think it's often what happens to specifications. They start off being quite accessible to users, but as they mature, then for the sake of implementers, the language gets more and more precise, but also more and more obscure. So they are there. Have a look at them if you want, but they are quite difficult to read and interpret these days. If you like textbooks, I'm afraid the news is not very good. There are a couple of OpenMP textbooks, but they have not really kept up very well with recent additions to the specification. So the first book I mentioned there just covers the basics up to version 2.5. The second book covers up to about 4.0, I think. So both of them are, even if you have both of them, they're still somewhat out of date with respect to the current specifications. Okay, so compiling and running OpenMP programs in practice. The good news is that you almost certainly don't need to install or do anything very special, because OpenMP is built into most of the compilers that you're likely to use, at least as long as you're operating in sort of high performance computing or desktop computing world. Embedded systems is another. Embedded processes are a bit different, but for high-end processors, then the situation is very good. Almost any compiler you're likely to come across has OpenMP built into it. So to compile an OpenMP program, you need to add a flag to your compile and link commands. So that flag is specific to the compiler. So for example, it's -f OpenMP for GCC or G-Fortran, for Clang, for the Cray C++ compilers. Other compilers are different. It's -H OMP for Cray Fortran, -MP for Clang, -Q OpenMP for Intel compilers. So you just have to read your compiler. If you're using some unusual compiler, you just have to read the documentation and figure out what that flag is to enable OpenMP. The other thing that we need to think about before after we've compiled a program and before we run it is how many threads it's going to be used. There are various ways to do this, but by far the easiest and most common way to do this is to use an environment variable. So the number of threads will be used is effectively determined at runtime, okay, not at compile time, by setting that environment variable before you execute the program. So for example, I can type on my command line or in my batch job script, export OMP _ num _ threads equals 4, and then by default, any subsequent OpenMP programs that I run will use 4 threads for all their parallel regions. And then when you run it, you just run it in the same way as you would run a sequential program. You just type the name of executable. So there's nothing different to running sequential programs in that respect. It's not like MPI. OpenMP doesn't require a launcher program like MPI run or anything like that. Okay, so we'll get on to practical exercises after lunch, but just the first thing I'll get you to do is just make sure that you can compile or run a trivial Hello World program, and get used to the idea of using the environment variable to change the number of threads. Okay. Any questions? Okay, so I realized that was a lot of me talking, and I've overrun my slot slightly. But I think we'll still have a full half-hour break now. So I will start again at 11:45 UK time. And I'll be back then, and then we'll get into the actual syntax of how to write parallel regions in OpenMP.